Hello and welcome to this online lecture. My name is Susan Conway and I'm a CNRS researcher from the Laboratoire de Planètologie et Géodynamique, so Planetary Science Lab, based at the University of Nantes in France. And today I'm going to talk to you about the history of water on Mars through its geomorphology. What do I mean by geomorphology? Well, I mean the landscapes and landforms that we observe at the surface. And I'm going to hopefully also explain to you how these landscapes and landforms give us clues about the climate and the evolution of Mars in general as a planet over its lifetime. So the lecture is going to be divided into two parts. The first part, I'm going to talk about ancient Mars, so Mars 3 or 4 billion years ago. And the second part, I'm going to talk about modern Mars, so Mars at the present day. Now, before I start, I just want to give you a few facts about Mars that are going to come up as relevant throughout the lecture. So just so that we all start with the same basic knowledge. Mars is smaller than the Earth and less dense than the Earth, which results in approximately 1/3 gravity acceleration at the surface. Mars is generally colder than the Earth, so the average surface temperature is minus 50 degrees Celsius. The range is also enormous in temperatures, ranging from minus 130 Celsius to nearly 30 degrees Celsius. And this is partly due to the thin atmosphere, which is the next point, but also its greater solar distance. The thin atmosphere has a pressure of around 6 to 10 millibars, which compares to about 1,000 millibars on Earth. This is one of the factors that comes into play with the huge variations in temperature I just referred to. Now, this atmosphere is different from the terrestrial atmosphere. It's a majority of CO2, carbon dioxide, 96%. There are other minor species, and amongst those is water vapor. And water vapor accounts for less than 0.1% of the Martian atmosphere. Now, both carbon dioxide and water are found as ice on the Martian surface, but they transform straight from the gas phase to the solid phase without passing through liquid phase, so they sublimate and condensate. So there is no liquid CO2 and no liquid water stable. And I'm going to talk about the stability of liquid water a bit more in the next few slides. And interestingly, the seasons are similar to on Earth because there's the same axial tilt. So there's spring and summer and autumn and winter as we find on Earth. Another interesting difference, geologically speaking, is that there's no plate tectonics on Mars. But what that means is that the surface doesn't get recycled through the mantle, and the result of that is that we can see surfaces, so rocks and sediments that have been at the surface of Mars for billions and billions of years. And this is not the case on Earth. We can go back to the Cambrian period on Earth and maybe slightly into the Precambrian, but not very much further than that. So on Mars, we have access to this really long geological record. Even though there's no plate tectonics, there are two distinct parts of Mars, two distinct surfaces on Mars, outlined by the dichotomy boundary, which runs approximately just a little bit north of the equator, where we can divide the planet into the northern lowlands plains, which is a younger surface, fewer craters, and the cratered southern highlands, which is at a higher relative elevation. And as the name says, there's lots of impact craters. And this is where we find the oldest surfaces on Mars. So to jump straight in, this is our current picture of water over Mars's history. This is a diagram taken from a paper by Elman et al. In Nature 2011. And what I'll do throughout the lecture, just to note now, is that whenever I've taken images from papers, I'll cite the reference by that image, so you can go and look up those papers if you want. So here, this schematic diagram, what you can see is that along the bottom, you have time before the present day. So the present day is on the right-hand side of this diagram, that's 0. And then this is billions of years, so giga-years before present day. And what you can see up the y-axis is a variety of different surface processes. And at the top are the names for the different periods on Mars. So I'm going to be talking using the names at the top, Noachian, Hesperian, and Amazonian throughout this talk. And these are the main periods. These are the main periods where we can see different sorts of activity of water on the Martian surface. So to give you a brief history of Mars's evolution over this time period, we start around 4 billion years ago. And what you can see is there's lots of things in each of these boxes 4 billion years ago. So Mars at the start of its history had a magnetic field which stopped just before the Noachian period began, more or less. And during the same time period when Mars had a magnetic field, we also have the large impact basins that we see at the surface today formed. So the northern lowlands could be, the Borealis basin could actually be an impact basin, though that is debated. But we do see Hellas, Argaea, and Isidis, which are the 3 largest impacts visible at the surface today. And these were formed in the Noachian period on Mars, just after the late heavy bombardment. It's thought that during the same time period that volcanic activity was very prevalent. So we had most intense volcanic activity, notably with the largest volcano in the solar system, Tharsis volcano, having been built during this time, but also the other volcanic provinces you can see are on Mars as well, such as Elysium Mons. So there's lots of energy being put into the system on Mars at the moment, surface. So there's lots of exchange between the surface and the atmosphere. The fact that Mars had a magnetic field means that the atmosphere was being protected from the solar wind. So in fact, we believe that early in Mars's history there was a much higher atmospheric pressure on Mars as well. So that's actually really important because that means that we can probably even bring water to be stable at the Martian surface. So what we see during this early time on Mars is that a couple of lines of evidence that point to a liquid water being very common at the surface, valley networks, which I'll describe shortly in the next few slides, and alluvial fans and deltas and paleo lakes, these dotted lines on here, which span from Noachian all the way into the Hesperian, all the way up to the Amazonian. Another important line of evidence that I won't be talking about in detail, but it is really important piece of evidence backing up the geomorphic evidence. So the geomorphic evidence for water comes in the form of these landforms and landscapes, is that of the mineralogy of the surface, that the terrains dated to these early epochs on Mars. And what the mineralogy or chemical composition of these landscapes tell us is that there has to have been water around to explain the alteration, so the chemical degradation of the mineral species. So what do we find? What does this actually mean? We find phyllosilicates, so clays, which require long periods of water alteration in order to form them. And these are all dated to a similar kind of time period to when we find these valley networks, which is what the bottom panel is telling us. Now, as we progress towards the present day, we transfer from this very active period with lots of different geological processes towards this period where there's pretty much nothing noted. So we go from a wet early Mars and I've written here warm in commas, inverted commas. That's because how warm early Mars was is under debate. And then we transition to the Amazonian, so the present epoch, where there's very little activity of liquid water, and I'm going to talk a little bit more about this towards the end of the talk. We have no magnetic field, so low atmospheric pressure, there's normal impact rate, there's minimal volcanic activity, and we don't have any evidence of these large aqueous systems. And also we have no evidence for the production of alteration minerals during this time. So Mars evolves from a relatively habitable planet towards what we see at the present day, which is a sort of desert-like surface. So just to clarify one of the points I made earlier, this is the phase diagram for water, and what we're plotting here is temperature along the bottom axis and then pressure along the y-axis. And what you can see across here in red is 1 bar, so that's terrestrial pressures. And in here, this is the Martian box. So actually, this should be transposed a bit further down because it should be partial pressure of water vapor. And what we can see is that Mars, though for most of the time, Mars water should be frozen, it is possible to achieve the triple point of water under exceptional conditions, even at the present day. And if we increase, as I said before, Mars's atmospheric pressure is believed to be higher in the past. So if we increased, we go upwards, we see that we actually improve the possibility of having liquid water. So liquid water is possible at the present day in very small quantities, transiently. But if we are able to raise the atmospheric pressure, you can see that the chances of getting liquid water are very, very much improved. The next slide here shows instead the phase diagram for carbon dioxide. And this is quite a common question that people ask when we show landforms carved, that we say are carved by liquid water on Mars, is that, well, the other volatile species on Mars is carbon dioxide. Why can't we have liquid carbon dioxide forming valleys and alluvial fans? Well, the very simple reason is that carbon dioxide is actually even further away from its triple point than water. So here you have the same kind of phase diagram with temperature across the bottom and pressure on the y-axis. And what you can see is the triple point for carbon dioxide, even though it's only at minus 56 Celsius, which is a temperature that you find quite commonly on Mars, and is exceeded quite commonly on Mars, you need a pressure of 5 bars, so 5 times the atmospheric pressure on Earth's surface in order to get to that triple point. And as I showed you before, Mars's atmospheric pressure is several thousand times lower than that. So it's very unlikely that you would ever get liquid CO2 at the present day, but even under past atmospheric conditions, when we think Mars's atmosphere was thicker, we never reach 5 bars. It's not a plausible surface pressure for Mars. So just to round that off, essentially, when we talk about liquids on the surface and evidence for liquids, it's liquid water and not liquid CO2, and there's no other species that is present in sufficient quantities at the surface to explain these fluid landforms. So to get on with the geomorphology part of this talk, here is an image of the Martian valley networks. This is what they look like from orbital imaging data. And what you can see on this image is a series of a network contributory network, where smaller channels lead into bigger channels, which lead into bigger channels. And this is a very classic arrangement of channel networks and valley networks on Earth, where you have this contributory nature. And what you can also see very nicely from this image is that they are distributed very evenly across the terrain. So they have a relatively high drainage density. And you can see that they're interrupted by newer impact craters. So there are, for example, here's a very nice image. You can see the ejector from impact crater here that lies directly on top of these valley networks. So they're hidden by more recent impacts. Now, actually, these more recent impacts are really useful because even though they hide part of the geomorphology, they allow us to date the age of these landforms. How do we do that? Well, we assume a bolide production function through time, and what we can do is predict the expected number of craters for a terrain of a given age. And so this gives us an age for these valley networks about 3.8 to 3.6 billion years ago. And the fact that these networks are found everywhere on the surface of this age, as I'll show in the next slide, attests to this a climate which must have been much wetter, must have allowed precipitation, distributed water sources. Otherwise, we wouldn't have this network that fills up all the space on the surface. So this is the distribution of Martian valley networks across Mars's surface. And the important thing to note here is that the dark gray areas are terrains that are younger than the Noachian, so we wouldn't even expect to see valley networks there. The light gray terrains that are old enough but don't have valley networks, as we might expect. So the dark black lines are the actual networks themselves. The blue lines indicate the sort of density in the regional area, and the yellow, this is a really important thing to note, are the detections of clay from orbital data. And you can see that where there are clays, there are also valley networks, and we think these two things are related, that you need the water that comes in to create the valley networks in order to have the long alteration period with water that you need to make clays. Now, I just want you to notice here, this is a region called Arabia Terra, and you'll notice that there's a large area with either low density or no valley networks. And this seems to go against the hypothesis that valley networks were forming everywhere. And I'll come back to this later. So remember this name for this area, Arabia Terra. Now, the fact we don't see any valley networks here, so this is the South Pole down here at the bottom, and so this is the near polar areas. This is actually probably due to resurfacing, so deposits of ice and other things on the surface hiding the Noachian terrains. So what other evidence do we have? So after the Noachian period, so after the early warm and wet period, we also find another important aqueous system, evidence for fluvial activity, evidence for water running over the surface, eroding sediments and depositing them again. And these are fluvial depositional environments. And what do I mean by this? Well, I'm talking about alluvial fans, I'm talking about deltas, and I'll explain in the next few slides what I mean by these two terms. But essentially, these are depositional, these are stacks of sediment that are laid down by rivers, and they're actually really important because actually within these sediments, which are now sedimentary rocks at the surface of Mars, we can investigate those rocks and find out the environmental conditions at the time when these fans were actually forming. So fans are actually really, really important archives of past environmental conditions. And we know that these are dated to after the valley networks were forming. And because these are so important NASA has sent both the Curiosity rover to an area with a fan and paleolake deposit, so Gale Crater, and Perseverance, the rover that's going to be arriving in February 2021, will visit Jezero Crater, which has a delta deposit within it. So linked to deltas is the existence of paleolakes. So deltas are sedimentary deposits into lakes. So, but we also have evidence for paleolakes without any kind of delta inside them, so basically channels leading to a depression. And so this is what you see on this map here, and you can see that they're extremely common as well. So not only do we have these fan deposits, but we probably also have these craters or other depressions filled with sediments, which are much more common than the fans or fan deltas. And these are so Gale Crater and Jezero are examples of this as well. And so these are also another place where we can go and find out more about the this part of the history of Mars, when after the valley networks are formed and before Mars dried out, as to how the fluvial system was working. So what do delta deposits look like on Mars? And this is probably the most beautiful example from the Martian surface. This is Everswaldy Crater on Mars, and this is a very beautiful delta deposit. So up here is the source, so the water would be flowing from up here, and this is the crater floor on the right hand side. And what you can see is these series of channels, distributary channels, so channels that go away from the apex, and a huge number of these lobes, and within each of the lobes you can see layers and layers of sediment stacked up. And this is very similar to delta systems on Earth. So this is the Mississippi Delta as an example, which is a currently active delta system, where you would see, if you took away the water, you would see this kind of thing. And you can see the distributary channels, similar again, and these different lobes, which indicate different sedimentary deposition at different times. So this is kind of the most beautifully exposed delta on Mars. Most of the other deltas that we see on Mars look more like this. So they're much smaller and slightly harder to identify. They simply form these arcuate benches at the exit of fluvial valleys. And in the example on the left, you can see these series of layers being exposed at the toe of the delta, which is probably caused by the erosion of this actual delta itself. And on the right, a false oblique view of another stepped delta system. Again, you can see the channel, the valley, sorry, exiting here, and that very nice flat-topped stepped delta here. So these flat tops are thought to represent the high water level in the actual paleolake itself. So we actually get both the sedimentary record and information about how much water was present in these paleolakes at the time when these deltas are forming. Now, the really important thing is that in order to form a delta, you actually do need water to be present at the time as it's forming. So we need standing bodies of water. So the water, it can't just be transient, periodic existence of liquid water at the surface. It has to be long-lived standing bodies of water, which is a much more habitable environment, more friendly for the existence of life than episodic flows that just drain away as soon as they happen. So that is more like the case for alluvial fans. So alluvial fans, here's an example from Death Valley on Earth, and as I'm sure you know, Death Valley is one of the driest places on Earth, and these fans, nevertheless, are caused by flowing liquid water, built up over very long time periods by episodic runoff. So very infrequent storms causing water to collect in the catchment area and then drain off, transporting sediment onto the fan. And we see the same kinds of alluvial fan systems on Mars. Here's a very nice example. On the left-hand side, you can see the catchment areas are relatively small, and you have the fan apexes, and then the channels lead out away from the apex. And we think that, and here's another couple of examples on the top right, one where you have alluvial fans coming out from all around the crater. And here's a zoom in of one of those alluvial fans here. You can see that classic radiating structure. And so for these types of systems, we don't need constant runoff, although alluvial fans can be made in humid environments as well as very arid environments on Earth. So there's no prerequisite for the environment to be dry or wet particularly, but they don't give a very strong constraint on the duration of the water flow, unlike deltas, which give you a very strong constraint. You must have standing bodies of water for a delta landform to form. So these alluvial fans give us precious information. They tell us about the environment. The sediments within them tell us about the environments at the time that the fans actually formed, but they don't mean long-lived liquid water at the Martian surface. You do need liquid water, but every so often, not permanently. So now I'm going to take you to Gale Crater, where the Curiosity rover, or MSL, landed. This is Martian globe to show you with the location of Gale. This is an actual image of Gale Crater. You can see there are valleys leading into Gale Crater, noticeably one up here as well. If you've got good eyes, you'll be able to see it. It's Peace Vallis up here. And a mountain in the middle called Mount Sharp, again with valleys running off Mount Sharp itself. And this mountain is thought to be just entirely made up, almost entirely made up of sedimentary rocks. And from orbit, there was evidence of aqueous minerals in the area where Curiosity actually ended up landing. So this is a view of the landing site and the path that the rover has taken over its lifetime. And you can see that one of the units is called the clay unit, and these clays have been identified from orbit as a sign of a lake. So what we think is going on here is that we had a lake in the bottom of this crater, and actually inputs from the valleys and catchments are both from the mound and from the crater rim. And this story is supported by the rocks and sediments that actually Curiosity has actually been able to observe in situ. So the story that we can tell from the geomorphology is backed up by the actual in situ sediment analysis by the rover. So this is a sort of stratigraphic column of the units that the rover has been visiting and ordered by age. And the rover started down in this part of the stratigraphic column, which Yellowknife Bay is one of the first places it visited, and that is an area dominated by mudstones and sandstones, as we might expect in a lake on Earth, where you have episodic inputs of sediment from nearby rivers, which are the sandstone units that stick out here, and the conglomerate units here. And so this is an image of those units here, and what we can see, I'm going to show you next, is the conglomerate units. So this is an image of a conglomerate on Earth where the pebbles are imbricated because of the flow direction, and you see the same in the conglomerates we see on Mars, that they're lined up in the direction of the water flow. This is another image of one of those conglomerate units observed by Curiosity on Mars. And the really great thing about actually being able to see these sediments in situ is that we can actually start to make measurements like we might do as a geologist on Earth in terms of grain sizes, and then from that we can actually consider the types of flow and flow rates and flow depths that we might need to transport pebbles of this size on slopes of this magnitude. And so we find flows of the order of less than a meter deep, discharge rates of 1 to 10 meter cubed per second, which is very consistent with the sorts of things we might expect on alluvial fans on Earth. And in fact, what we think is that these alluvial fan deposits are originating, in fact, from Peace Vallis, which is located up to the top left of this image. So the majority of the other rocks that the rover has encountered are very finely layered mudstones and sandstones, which are very typical of lake deposits. So exactly what we expected from the orbital data. And this is one of my favorite images of outcrops from the Curiosity rover data. This is mud cracks. So what we think is happening here is that the lake dried out for a certain period. So something like the salars in the Atacama or the Playa Lakes in Death Valley, that there's occasional floods that there are floods that then dry out, and these sort of mud cracks are observed all throughout the traverse and are thought to be evidence of drying out in this lake region. So what does this all tell us? So we have these valley networks, we have these alluvial fans and deltas and paleo lakes, and initially researchers said, well, this must, like it does on Earth, attest to a warm and wet climate. So on Earth we have very similar warm, wet climate where liquid water is very abundant and is responsible for a lot of erosion and transport on the surface. But there's a problem with this warm part, in that back 3.5 billion years ago, the sun was actually a lot weaker, and what that means is even though Mars had a denser atmosphere, as I showed you before, that brings water back into its stability, it would have been still a lot colder because the sun was putting in a lot less energy. So we have trouble getting to that triple point because we have trouble getting enough energy into the system in order to support these warmer, so 273 Kelvin surface temperatures. So what researchers suggested in order to try and overcome this problem of energy input is that that we could have actually had a cold and icy climate, where you have basically an ice cap that is all across the southern highlands, because when you have a thicker atmosphere, it's colder as you go up in the atmosphere. And so what would be happening, instead of getting continuous rainfall and runoff and formation of these fans, lakes and deltas, you actually just get periodic heating caused by volcanic eruptions or elevated heat flux or impact events. And it's those punctual events that causes melting of this ice cap. So basically subglacial melting. And so the valley networks are actually formed underneath a giant ice cap. This is kind of the image of that, where so the geothermal flux becomes elevated, and then you end up with melting underneath the ice cap. The only problem with this icy highlands hypothesis is that it isn't really supported by the geomorphology. Essentially, there are a few valley networks that we find at the surface of Mars that are consistent with subglacial valley networks, but the vast majority of them are actually consistent with normal subaerial valley networks that we find on Earth. And we don't see widespread evidence for glaciers on the surface at this time. Another point in support of this icy highlands hypothesis was this gap in Arabia Terra that I pointed out before. So if you have an ice cap, the gap in Arabia Terra in the valley networks is easy to explain because this is an area of lower elevation where you might not have expected ice to have actually occurred. So you don't get valley networks because there's no ice there. However, the gap in the valley network distribution in Arabia Terra could actually just be to do with preservation potential. So more detailed recent studies have shown that across Arabia Terra there are lots of inverted channels and inverted sedimentary deposits. So what that means is that in fact, instead of the valleys being preserved as holes in the ground, they're actually been eroded away, preserving the channels as raised parts in the ground. So this means probably the terrain is a bit softer in this area and has been more easily eroded. So the Noachian valley networks, instead of being preserved as valleys, are preserved as a positive relief. So we don't need an ice cap to explain this gap in the valley networks. Also, recent climate modeling studies have been able to generate sufficient runoff and hydrological activity with a sort of intermediate case. Instead of it being really warm and wet, it's kind of slightly warm and wet. So with annual snowfall and melting that snow, you don't need full ice caps, but instead you snow on an annual basis, and then that melts, produce the runoff. And with those conditions, you can actually, even with the faint younger sun, you can still produce enough water to explain the sorts of valley networks that we see at the Martian surface. So perhaps, in fact, we're looking at a situation more in the middle between the icy highlands and the very warm, wet early Mars. So I hope that I convinced you that there was plenty of surface water in Mars's early history, and that that wet period was actually quite long-lived, and we see a transition via the occurrence of alluvial fans and deltas to a drier present-day Mars. What does this mean? Well, in the Noachian period, or pre-Noachian period, when the valley networks were forming, we probably had almost constant surface water. When we have deltas and paleolakes, we're also in an environment that's quite wet. So these form very good environments for development and persistence of life. But as Mars dried out and we start to get periodic systems like alluvial fans, whether life could survive at the surface is a bit more of an open question. And it is really this period that's under active investigations, and we're relying on orbital and rover data to help us build up a fuller picture and a more complete picture of the hydrological environments on Mars during this time. So this concludes the first part of the lecture. So for the second part of the lecture, I'm just going to bring up this slide again about water over Mars's history. And we're going to be talking about, this time, this period right at the end, the late Amazonian, so the present day surface conditions and the surface conditions over the recent past, where Mars is believed to be cold and dry. So I'm going to take you through a little story which has kind of been my journey as well through part of my academic career, and that is to talk about these features that are called gullies on Mars. And these were first discovered in Mars orbital camera images. So this is on NASA's Mars Global Surveyor. and reported in Science in the year 2000. And the title of this paper was Evidence for Recent Groundwater Seepage and Surface Runoff on Mars by Mike Malin and Ken Edgett. And this is big news because, as I explained before, liquid water is not believed to be present at the surface of Mars at the present day. So the fact that we see these gullies, these landforms that look like features carved by liquid water on Earth, attests to the fact that the liquid water could also have been running over the surface of Mars. And here's some more detailed images of what they look like on Mars. So what are we looking at? We're looking at systems that have a series of tributaries that lead downslope into a channel or multiple channels, and those channels have a fan deposit or debris apron at the end. So these are integrated systems, as we find in fluvial systems on Earth, where we have tributaries that lead into channel or channels that are then, which are incised into the surface, which then deposit onto a debris apron or fan. So this is a very classic arrangement that we find in water-driven sediment transport systems on Earth, fluvial networks, gullies, whatever you want to call them. The term gullies was used in this first paper, so has been continued to be used afterwards, somewhat controversially, but we have to stick with it because that's the name that was given initially. So why did the authors actually, in this first paper, talk about groundwater? Well, as I said right back at the beginning, liquid water is not stable under Martian conditions, so you have to find a way of generating these flows at the surface without water being stable at the surface. And the most logical and easiest way to do that is to get the water from the subsurface and bring it up to the surface to form these features. So this is why they were initially thought to be groundwater seeps. Now, the geomorphology of these gullies isn't very consistent with that because they're found originating at the top of hill slopes, where getting groundwater up into the tops of these hills would be really very difficult. And so quite rapidly after the publication of this paper, groundwater became the least favored theory. I mean, there's no actual way we can disprove it's groundwater, but it seems pretty unlikely, given the situation of some of these gullies, that they're driven by groundwater. So this was the reason that Ken Edgett, Mike Malin and Ken Edgett ascribed these features to the action of liquid water. It was their extreme similarity to gullies on Earth. So on the right-hand two panels, there are gullies in Svalbard and in Iceland, and on the left two panels, you have gullies on Mars. And what you can see is the scale of these features is very similar. So we're looking at kilometers features. And in fact, on Mars, gullies are found on steep slopes of all types. So most steep slopes on Mars are caused by impact crater walls, but you also find them on mesas, on valley walls, on steep dunes, all sorts of steep slopes. So they're not dependent on a certain surface type. They're found on all sorts of steep slopes. And another important point as well that you can see in this image is a very small impact crater at the bottom of this particular fan and this particular gully on Mars. But on the whole, there are very few superposed impact craters. And as I talked about right at the beginning, impact craters, the number and size of superposed impact craters tell us about the age of the systems. And the oldest systems that we have investigated on Mars date to at most 5 million years ago. So we are pretty sure that they're probably a lot younger than that. And we know that they've been active over prolonged periods of time because we see both active parts of the fan areas, so here, for example, as you do on Earth, here, and more are older, less active parts of the fans, which sometimes also have impact craters superposed on them. So we know that these systems are repeatedly active. That's very similar to on Earth. We have these gullies on Earth, we have active parts of the depositional fans and inactive parts, showing that there's been buildup of the sediments over time. And we know that these gullies on Mars, they were active over prolonged periods of time, episodically possibly, and in the last few million years, when liquid water is thought not to be stable. So this is the most complete picture we have of their distribution. This is a survey done using 6 meter per pixel context camera images, done by Tanya Harrison and published in 2015. There's probably a few different things that are there's probably a few more gullies that need to be added and maybe a few that need to be taken away, but more or less this is the most complete picture we have. And so there are thousands and thousands of these gullies across the Martian surface, and you'll notice that they're absent in the mid-latitudes, they're absent, sorry, in the equatorial latitudes, and are concentrated in the mid-latitudes in both the north and south. The reason there are fewer in the northern hemisphere is actually there are fewer steep slopes, there are many fewer impact craters. So the reason there are fewer in the north is just the absence of steep slopes rather than any other factor. And so this latitudinal distribution in gully landforms led researchers to think of a climatic reason for the origin of gullies, for the formation of gullies. Because when you see a latitudinal distribution, that implies a reliance on temperature distributions on the surface of the planetary body. So, as I said, at the present day, water is only transiently stable, and we can actually reach the triple point. We saw the phase diagram that I showed you right at the beginning, so this is another version of the same phase diagram here, but this time the Mars regime is put on the partial pressure, so these are the average conditions, partial pressure for water vapor. And you can see that it's quite a long way away from the triple point under average conditions. And what you see on the right is actually a plot. So this is latitude and longitude, so a global map of Mars. And what the authors have done is run a global climate model and calculated the number of days when transient liquid water could exist at the surface and where. And if I superpose those latitudinal bands where we find gullies, the two don't really match very well. These two blobs here are the two impact basins of Argaea and Hellas. And actually, we don't find very many gullies at the bottom of these basins because there aren't very many steep slopes. So this doesn't match very well. So what researchers have had to call upon is the fact that Mars actually undergoes huge shifts in its climate. Why is that? Well, that's because Mars's axial tilt varies enormously in time. So we had down here time, a million years before present, and obliquity, so the axial tilt of Mars on the y-axis, and the Earth is this squiggle down here. So you can see that the Earth varies between 22 and 24 degrees in terms of its axial tilt, whereas Mars varies between values of around 15 degrees and 35 degrees. Now, if you think the axial tilt variations on the Earth, 1 or 2 degrees, actually lead to glacial and interglacial periods, so huge swings in the stability of liquid and solid water across the surface of Earth. And on Mars, we can imagine that with such huge shifts in obliquity, that this would also have enormous implications on the stability of and distribution of ice across the surface, ice and water across the surface of Mars. So this is what drove researchers to go from looking at groundwater to explain gullies to thinking of a more climatic reason to explain the origin of gullies. So just a quick note, we can actually calculate the orbital parameters of Mars back to 10 million years ago, but not any earlier. And that's actually okay for gullies because we think they only date to maybe 5 million years ago. So what do we think is happening, more or less? So we know that Mars has two large polar ice caps made of water ice, and that's the situation at the present day, here and here. The atmosphere is relatively thin and it has low humidity. What would happen at high obliquity? Well, those polar caps would get pointed towards the sun once every year, and the average temperature in the polar regions would actually be higher than it is at the present day. So that would produce a net sublimation of the polar caps, redistributing the ice to lower latitudes, as you can see in this schematic diagram. What that means is you have much higher humidity in the atmosphere as the ice is transported around. A thicker atmosphere, because we actually think that part of the south polar cap is composed of CO2, so we have a thicker atmosphere. And this probably means that we might achieve liquid conditions, temperature, pressure conditions conducive to liquid water more often. So this is what we think is, this is what people think might be happening for gullies on Mars, is that in the mid-latitudes where we find these gullies are most common, the pole-facing slopes are actually the coldest in winter, so they act as cold traps for the water ice. In summer, they're actually some of the warmest places on the planet. So they go from being very, very cold to being very, very hot very quickly. This is the most conducive conditions to produce melt. And so surface melting can produce debris flows, but this also could be an explanation for groundwater release, because if your groundwater reservoir is plugged by ice, then this would be the time periods when you'd expect the water to be released from those aquifers as well. And so this explains why this kind of model of high obliquity conditions can explain the distribution of gullies on Mars, but not only their distribution in terms of latitude, but their orientation trends. So in the mid-latitudes, the majority of the gullies are pole-facing, whereas, for example, the preference is much less marked at either the high or the low latitudes. And you wouldn't expect any gullies at all in the equatorial latitudes. So this is the polar latitudes up here and the equatorial latitudes down here. So this was basically the state of affairs around 2004, 2005, etc. And then in 2006, so we have we have a few Mars years of data of monitoring of the gullies at this point. And what was found by the Mars Orbital Camera again was that some of the gullies had new deposits, these bright new light tone material, as this paper reports. And first of all, so this kind of throws a spanner in the works for this is a problem for if these gullies are formed by liquid water, because we know that liquid water is very unlikely at the present day. So if they're formed by liquid water, something weird is going on, because they shouldn't really be active at the present day. They should just be fossil landforms, essentially. But what people said was, well, maybe these light dome deposits, which don't seem to have any topography, just seem to be a surface, very fine superficial deposit. There's nothing else apart from a bright color that appears. So that maybe, in fact, as this modeling study by John Pelletier shows, these could just be dry flows. So these are the modeling results where they model both dry granular cases and Our liquid water case is actually the morphology of the dry gully flows is a lot more similar to the morphology of the bright deposits than the water flows. So these could just be dry mass wasting deposits, and they don't need anything special or any liquid water or anything. So these could just be modifications of the gullies after they initially formed, rather than the actual formation mechanism. So these activities may be nothing to do with the formation of a gully in the beginning. However, what we've seen with much longer period of observations over the last 15 years or so is that not only are these new bright deposits occurring, but there are other changes happening, such as in the example on the left, you can see that between 2009 and 2013, a new channel formed in this particular gully, and in 2018 that channel grew even bigger, so we're actually getting significant erosion into the surface. And on the example on the right, you can see there's a huge rock being transported down slope in this particular event, and other smaller rocks being moved about. So there's, you know, the longer term monitoring has revealed that the activity in these gullies is actually a lot more than we thought initially. So the sorts of volumes of sediment we can see moving through these systems are, if you calculate the typical rates of activity, so once every 10 years, let's say, and you can generate gully systems within the lifetime, easily within the millions of years that we think that, you know, we think that age is around the hundreds of thousands, millions of years. You can easily create the volumes needed using the sorts of flows that we see at the present day. This is one of my favorite ones. Sorry, it's on its side. So downslope is to the right, but you can see this huge lobe of material being deposited at the bottom of this gully system, and you can also see the channels emptying at the top of the system. So this is a really nice image, and it shows the number of blocks and the sort of meter scale thickness of the lobe at the end. So these are significant sediment transport events that, if you sum them up over the sorts of lifetimes we expect for the gullies, you can actually explain the gully morphologies themselves. Now the sort of hic, I suppose, with the water hypothesis, I mean, maybe the transient liquid water could explain some of these gully systems, but the hic is that when we know the timing of the activity, which is not actually in very many cases, it happens in winter when carbon dioxide frost is on the surface. So this is what this chart is showing you here. This is the latitude and the black bars are when the first bar is when the image without the change, and the second vertical bar is the image with the change, and so the horizontal bar shows the period of time when the activity could have happened, and it could be anywhere within there. And so in the bottom, this is Elizabeth, so solar longitude, where I've translated what that means for you here. So 0 is the autumn equinox in the southern hemisphere, winter solstice is 90, etc., etc. And so you can see in blue, this is a sketch of when CO2 ice is present continuously across the surface as a continuous layer. And you can see that it's continuous to around 50 degrees latitude. And then after that, actually, you get discontinuous frost, thinner frost deposits. And you can see that the gully activity is occurring when you have this discontinuous frost on the surface, and not when you have this continuous slab of CO2 ice. And so the temperatures when CO2 is on the surface are in excess of minus 100 Celsius, lower than minus 100 Celsius, sorry. And so it's very unlikely liquid water could be responsible for these activities. So this is just a sort of schematic of what that looks like on a global scale. This is the CO2 ice that I'm talking about are called the seasonal polar caps, and they can even be seen in telescopic observations from Earth. And so what we think is happening is that sublimation of the carbon dioxide could be responsible for these movements. And why do we think that? Was because we see other sediment movements on Mars caused by the sublimating seasonal cap. And so these images you can see here, these black splodges are actually deposits of dust which have been lofted by CO2 gas escaping from underneath a CO2 ice slab. And we think this could be happening in Martian gullies as well. So the solar insolation, the CO2 ice is semi-transparent, and so the solar insolation actually penetrates all the way to the regolith underneath. That then warms up, sublimates, causing gas to be released. That gas pressure breaks the surface, forming these black splodges that I showed you on the previous slide, and also carves away the substrate underneath to make these gullies. So this slab kind of activity requires you to have continuous carbon dioxide ice. And as I showed you in the diagram of activity, not very many of the gullies actually have this kind of occur. The activity doesn't occur when the CO2 ice is continuous. It could explain some of the gully activity seen in the polar regions, which an example is shown here of one of those deposits. But we have a problem in the mid-latitudes, is that CO2 ice is thin and discontinuous, and so the confining CO2 slab model doesn't really work in that case. So we don't have sublimation landforms on Earth to help us with this. We can't go out and observe the creation of gullies formed by sublimation in the field. So what do we have to do? We have to rely on lab work. So you can see a speeded up video of some lab work that was done a few years ago in simulated Martian conditions with CO2 ice. And we can also do numerical models to try and look at this. And this is something that I'm actually actively working on at the moment, is trying to understand how CO2 sublimation could actually work to form gullies. How can we transport boulders? How can we carve channels in sediment? And this is still a totally open question. So a conclusion for this second part is a precautionary tale, basically, that water-like landforms can probably be formed by other processes, so we need to keep an open mind and make sure that we take care when we're making an analogy with the Earth. And the upshot of this discovery of Martian gullies being probably formed by CO2, it could be water in the past, but it's probably formed by CO2, is that the sort of paradigm of Mars being a cold, dry, hypervarid environment is upheld. And we probably very likely don't have habitable environments near the surface of Mars, but that doesn't exclude habitable environments occurring in the subsurface. So that is really something that we need to investigate in the future, is what is the subsurface of Mars like. So as overall conclusions for this lecture, I hope to have shown you that geomorphology provides us with vital constraints for understanding the climate on Mars. So studying its landscapes and landforms can help us understand how the climate on Mars has changed through time. And using geomorphology, terrestrial geomorphology approaches, we can start to quantify erosion rates and processes. But as I just showed you in the case study about gullies, we need to be careful about directly taking insights from Earth and applying them to Mars or other planets. And the really key area of research in the future is going to be trying to understand what happened to all that water that was active early on in Mars as it got into the subsurface, and how that transition occurred between the precipitation, perhaps snow, that was going on early on in Mars's history, and then how that drying out happened. Was it really sudden? Was it gradual? I think we're finding that it was probably more gradual, but how long it took and exactly is still an open question. So thank you for your attention, and I look forward to answering some of your questions later on.